Hello everybody, and thanks for joining our joint webinar with our friends from Signalysis. Today we're going to mainly talk about end-of-line efficiency, how to increase that, and how to do end-of-line or production testing using a non-contact method with an intelligent automation. So in my short presentation, I'll be talking about what Polytec makes and what is the principle of the product that we're going to talk about, which is the laser vibrometry. What type of systems are available, and also why we are using a laser vibrometer at the end of line testing. And then we'll talk a little bit or briefly about connections. Then I'll hand off the mic to our friends from Signalysis. It will be Neil. So yeah, let's get started. So Polytec is a worldwide company. We've been in business since the 1967, mainly focused on laser vibrometry. We have 3 main offices in the US, and our HQ is located in Irvine, California. Besides laser vibrometry, Polytec is well known also for other non-contact measurement devices, such as the surface metrology and the length and speed. So all of these are using different technologies, but they're all known for high resolution repeatability and being a non-contact device. When we're talking about vibration, it's everywhere. It's in our life. It's at our home. The fridge is vibrating, the airplane. So everything around us vibrates at different frequencies. And in most cases, our goal is to eliminate or to detect that vibration using some sort of sensor that tells us if this vibration is within the acceptable values or not. When it comes to the data that we deal with normally from a laser vibrometer, it will be in terms of motion, and that motion can come into a velocity, displacement, and acceleration. So these are like the main 3 parameters that any moving part will exhibit when gets excited or pushed by a force. Then that data can be displayed in a mode shape, such as an animation, or what we call an operational deflection shape. Or it could be on any surface, such as a wave propagation on a skin, or any surface that would like to find a defect on, such as this surface right here. We can see the wave propagates through the surface, and if there is any impurity or any defect on the surface or underneath, it will be detected visually. And also the main 2 parameters that vibration gives us is the frequency response, which comes into a frequency value with an amplitude, as well as the time domain. These are like the main 2, I would call them output parameters of any moving component. Then both of these combined can be displayed in the full chart of time, frequency, and amplitude. Now, when it comes to the principle, so the laser vibrometer actually is a non-contact device. So as you can see here, the red beam, let me use that pointer. So when it comes to the signal that's being sent from the laser to the moving object, so it will touch the surface, then a returning signal will come back carrying some frequency component that is associated to the velocity of the moving part. And the demodulation between the send signal and the return signal, what we call the Doppler shift, this will be giving us the behavior or the velocity of the response along with the frequency. Then that signal will go into what we call a detector. Then it will be converted from optical signal into electrical signal. So this is kind of just a brief description on the principle of how the laser vibrometer works. There are a few types of laser vibrometers depending on the application. Some of them what we call out of plane. So imagine a surface or a flat panel that moves in and out. So that motion in the direction perpendicular to the panel, we will call it out of plane. The opposite direction, which could be in X and Y, it's called in plane. And there's another type of vibration that is called differential, where it gives us the relative vibration between two locations. And there is the rotational that is attached or associated with the angular vibration response. Then, so that's the type of vibration or measurement can be done. Then there is also types of scaling, because vibration could happen on microscopic level. It could happen on a scanning where we need more than one location. And in this case, it will cover the whole surface. And then we have the full 3D that allows us to measure all three axes, which means we get the full motion of any surface or any part in all three coordinate system. And then for any transient event, we have what's called the multi-point. It's multiple lasers that are pointed at the same surface to capture the response at once. When it comes to the out of plane, there is a single point, and the single point is just aim and shoot. Just imagine it as a non-contact accelerometer. And they come in different types and models depending on the application and the frequency, but they all measure from DC to a higher frequency depending on the selected bandwidth. And these systems can go up to 25 megahertz. And when it comes to velocity, we have the high velocity one that can be applied for the valve train application, for example. And if you have a device that is too small and you require some magnification with a camera, there is the VibraFlex family, which varies from standard laser all the way to measuring, let's say, a full building or a structure at more than 300 meters. But our focus today will be mainly on the industrial, which is the most cost-effective, simple, compact laser vibrometer. On the other hand, the scanning system could be a 1D or a 3D, and the output of these, besides the frequency response and the time domain data, we will get what's called the operational deflection shape, which can be used to validate any model analysis or finite element simulation. Okay, now why do we use laser vibrometer? I mean, there are a lot of sensors around, a lot of conventional sensors, but one of the main things that the laser is very well known as not affecting the mass of the structure to be used, because the natural frequency basically consists of stiffness and mass. So laser vibrometry has no effect on the mass of the surface. And as we can see here in this example, where the laser pretty much has 0 gram, as if you compare it to an average of an accelerometer that could have 10 grams of mass. Now imagine if you do a scan and you want to place multiple ones, then the mass of the surface to be measured will be changed, and all of the parameters, including deflection shapes and frequency response, will change. The other kind of advantage of using a laser vibrometer is it can be placed at any distance. You don't have to be at a specific location. It can be very close or it can be far away from the surface to be measured. It also has a small spot size. Here we're talking about microns. And that becomes benefit if you want to capture the vibration at two locations that are very close to each other, but they might behave differently. Then the other important kind of feature of a laser vibrometer, it doesn't care about the surface type. It doesn't care about the light reflectivity as well as the type of the surface, along with the conditions. So it could be hot, could be molten steel. The laser vibrometer still can capture the vibration response. High resolution in terms of amplitude. It has high accuracy and repeatability. and also covers large frequency bandwidth, as we discussed. It can be from 0 hertz all the way to 25 megahertz for the standard systems, and we have systems that can go up to 8 gigahertz if needed. And of course, here we're talking about end of line, so it's a seamless integration, and it can work directly in an end of line production testing. And most of our systems come with analog and digital outputs that you can use, whichever works, if you have a PLC or if you have just a digital input that accepts an Ethernet. When it comes to the laser types, there are two laser types in general. There's the standard helium neon, and there is the IR with a QTec, which is a patented technology by Polytec that has a few things been added to the standard laser vibrometer that made it even stronger, especially when it comes into end of line where you don't want to have any failing results under any condition. So the QTec is very well known for having a very high signal to noise ratio. It has no requirement for any surface treatment or any type of texture. So pretty much any surface can be placed on and it will give us a nice response of the vibration. Works at a short and long distance. Can be very close, it can be placed at a very long distance. And it gives the best vibration response even if it's not fully focused because it's a laser and generally lasers have a focus value, but the QTec system doesn't care if the laser is focused or not. It always gives a high signal to noise ratio. And one of the other important aspects of having the QTec is no dropouts. So it's very good to be used in a controlled closed loop environment where the signal is always pure and has no dropout in that return signal. It covers high frequency range. And these are kind of the main features of the QTec, the patented technology. Now, of course, for each integration, having a connection is very important. Generally speaking, for the IVS and the QTec or VibraFlex systems, they both come with analog and digital signals. So here's a small schematic of, this is the back of the IVS system, where it can be connected via analog. Either goes directly to any PLC or any control module that will accept the signal through one of these connections. So we have CON1, which is mainly used to power the system and to get the signal output. And that can be plugged in into any PLC or any sort of data acquisition. Also, we can use the direct analog output. So having the aid of this, what we call evaluation kit, this allows you to take this direct BNC of the velocity, acceleration, or displacement. That's what the old systems would have as an output directly into the DAC without having to go through any change in the signal or conditioning. The other simple method is just using a digital Ethernet. So it's an RJ45 that can be connected into any device or DAC that accepts Ethernet. So that's the other method. And of course, there are some more advanced, also easy to implement, such as the integrated macro programming, also the automation for interface, where this allows you to control the sensor externally. It allows you to collect the signal in a certain way. And also we have what's called the Polytec device communication, which works with a lot of programming languages. It comes with libraries that can be integrated for automation. So these are kind of, the basic connections and a brief chat about the different types of laser vibrometers. And at this time, I'd like to hand the mic to our friend, Neil Coleman from Signalysis. He works directly with the laser vibrometers and to end-of-line integration for a lot of cases where pass and fail becomes very important. Neil, if you're connected, the mic is yours. And thank you all for joining the webinar. Thank you.
Well, thanks, Osama. Hopefully, yep, am I connected? Everybody give me a thumbs up. So good.
All right.
Just a little quick introduction of Signalysis. We've been in the end-of-line test business probably since 1995. I originally founded Signalysis back in 1987 as I left a career in structural dynamics testing and a lot of mold analysis on space shuttle substructures in part of their fatigue certification program. Throughout that whole process, we were just day after day doing damage detection on the shuttle itself, and or maybe various substructures of it, and ended up developing some pretty cool technology where we didn't have to tear apart the system or pull out microscopes and other types of NDT or test methodology. We could just whack it with a hammer or shake it with a shaker and measure the response. Started that with in the world of IndyCar racing, doing some wind tunnel testing and so forth, and a lot of roller coaster testing back in my early days, as well as some rock concert monitoring. But somewhere along the lines, we started getting involved in more production test related things in the automotive industry. And about 2000, that really took off, and we were starting to get involved in how's the best way to get a vibration measurement on an assembly line and so forth. And somewhere along the lines, about 2000, we were introduced with Polytec and started using the IBS 300, the 400, the 500, and it just opened up a new world of applications for us. Granted, a lot of pushback early on, and even still today, some people have a quick knee-jerk reaction when they look at the price of a $500 accelerometer compared to a $12,000 laser vibrometer, all the way up to the higher priced QTec. But the return on investment in a manufacturing world when they're testing thousands of parts a day, it's a no-brainer. The accuracy, the repeatability, and be able to feed that data back into various Six Sigma studies and that kind of stuff just really pays for itself really quick. But somewhere along the lines, probably 2020 or so, we started using the QTec for applications. It used to be that when we were putting a laser on a casting, like maybe we're doing a transmission test, and as the transmission comes down the line, the laser comes down and points at the fixture, and the signal strength and signal noise isn't all that great just because it's a casted surface, and the single point laser would sometimes line up correctly, sometimes it wouldn't. So we would have to add a process in the manufacturing of the casting to come in and put a nice shiny smooth surface in on the part, cut that in, and then it worked pretty good. But until then, all of a sudden we started messing around with the QTec and realized that we didn't have to do that anymore. We didn't have to have a focal length and adjust things. So if the part was moving during tests, the QTec can handle that, and it's really been a game changer for the last few years in various applications and so forth. So, but I guess this slide just kind of shows a brief history of time. We end up working a lot with a lot of different customers, a lot of different types of applications, using the CQC product of ours, integrating to various sensors and so forth. But in pretty much every one of these applications you see here, we've had the opportunity to implement some version of a laser vibrometry type measurement. we build our lives and our business on strategic relationships with various integrators, sensor suppliers, strategic alliances with the company. And Polytec has been a very good partner of ours, and been very responsive to new applications that we've had that we want to, hey, will this work, and so forth. And they'll loan us a laser, or we'll go up to their facility, go to Germany, and work on an application just to figure out, hey, can we deliver the best solution possible? We pride ourselves in our knock your sock off service. So after things are integrated, new problems come along, between you and your customer, we work with you to make sure that that gets taken care of and the measurements are correct, data's fed to the right places, and so forth. We provide training, educational services, and so forth. A few of the applications you see there we've got involved in. We have medical application, medical devices, where we're maybe testing dental drills, maybe we're testing bone saw drills, and just various other kinds of type devices, medical devices that such as EpiPens that have to that talk to you and have feedback. We want to make sure that the tonality of that part under test is right, and we can use the laser to determine that. So in the end, our mission is to deliver the ultimate solution experience to our customers with unsurpassed integrity. And it starts at the very beginning, where we don't want to sell a system and integrate something until Osama and I have gotten together and we've proved it out that, hey, this will get the job done, and it will last a lifetime at the plant. So give you a few ideas of some of the ways we've implemented a Polytec laser over the years to make intelligent decisions with our IQC systems. It comes down to making sensor choices. There's all kinds of applications that go into an end-of-line test. There's vision systems everywhere. There's hardness measurements. There's a torque measurement sometimes where you can use the current draw and maybe as a torque sensor and identify actuator interference or too much just amperage, of course. Noise using microphones. Primarily, we like to use them if it's an airborne noise application. If it's structured borne noise, we would much rather point a laser at it and make that measurement, because in the manufacturing environment, you have a lot of background noises, and those background noises change from week to week, depending on how excited some line operators are about the game that was just played a few days ago, or some arguments going on, or just forklift drivers that like to run into things. It happens, and having the laser and being able to put the laser away is good. Surface finish is one of those areas that we're starting to get involved in. We've done a lot of brake rotor testing, but recently we're being asked, and as well as Polytec, hey, can you measure the surface of the finish that's being produced, and at 100% on the inspection line, and we can do that with the metrology systems. So there's a lot of different benefits to using the laser vibrometer. No moving parts is one of the biggest ones. For years, we've been taking accelerometers, advancing an accelerometer in to touch off the part under test. And that, for the most part, that really works good if you can control the actuator. But unfortunately, sometimes the air, it's a pneumatic actuator, and air pressure changes. Therefore, now today on this part, I'm pressing harder than I was on the part from the day before. Other things come into play is moving cables. Cables get broke. Maybe the customer doesn't, their operators on the line don't really pay attention. We put information tests in to determine a bad sensor, but as soon as the sensor cable breaks, the line has to stop. The maintenance needs to come out, look at things. They need to go to the stock room to find replacement cables. They don't have them. Now they're down for a period of time until they can go get some more cables, and we stock those, but it's normally not within the next 2 minutes that they get it. And so a lot of downtime comes with actuating an accelerometer into touching off a part. The other piece is where it's given us the opportunity to do a lot of applications where mass of the sensor does really play a role in the measurement. I've got a saw blade test. We'll show you a movie of it in a second. But it always comes to, the smaller the part, the better it is to use the laser and so forth. Frequency range is another big issue. As you advance the accelerometer to touch off the part, if it's a single point touch, you're probably going to get maybe 1,000 hertz of a good signal out of that. If it's a magnetic on a perfectly clean surface and a really nice smooth magnet and strong magnet, you'll maybe get 5,000, 6,000 hertz out of that test. The laser vibrometer immediately gives me 10,000 for the low end version, and can go all the way up to 100 kilohertz on high end applications and high end versions of the vibrometers. And as Osama would, I think he said something about, in the gigahertz range, or at least in the megahertz range, but we've never had to do production tests at that level. But it also gives us opportunity to hit hard to reach surfaces that you can't advance in and get. Maybe I want to measure inside a little groove or a slot that's exposed to the material, and I can't get an accelerometer down there, and the laser is the only way to go to get that in it. And it does a great job of it. Then there's other sensitive parts that maybe has a nice surface finish, and you don't want me advancing anything to touch off that part. The part moves a little bit, it gets a scratch, leaves an indent. That is certainly a concern for a lot of applications. Then harsh environments is another one. We'll show you something here just in a second on testing with in a steel mill and so forth. So basically, in the end, you get an accurate measurements, and your very repeatable measurements for a good gauge R&R in the applications. So I think I talked a little bit briefly about the higher price, yes, but return on investment is very high as well. You can walk in. There's been plants I've walked into with the laser vibrometer, can set up right there on their existing production line without any other interface except maybe talking to someone with the PLC to give me a start signal and send me over some serial number information for traceability. But it's quick and easy, and you're not going to get that in a lot of other applications. One of the big costs in any traditional accelerometer type testing is the use of actuators to advance in the part, the cables and so forth we talked about. The return on investment within a year of those kind of damages and failures that we've seen is huge. Wheel application where I'll show that to you in a second too, that where we're casting wheels, we're not able to, the customer's not able to pick up a damage or issue in their pour process that's creating porosity until maybe 30 wheels into a production, and that's a lot of scrap to have to throw away. Whereas using the vibrometer, we're able to detect the presence of that defect within the first 1 or 2 wheels, and they can immediately stop, do whatever repairs they need to make, and get back to doing what they need to do best, and that's produce train wheels without porosity. Center metal parts is the same thing. Those of you that are familiar with the sintered metalling process. You'll press your powdered metals into a mold and send them down a conveyor line, send them through an oven. Then when it comes all the way out, you'll turn around and do some mag particle inspection probably. At that point, you have a whole conveyor line full of materials of parts that you pressed out. Well, if it turns out that your press has run into a problem and it's causing cracks to be, or the part to be damaged in any way, you won't find that out until that probably 2 or 3 hours down the line. Whereas we've developed a method using the QTec and to identify those cracks right as it comes out of the press, the powder metal press. So it works pretty good. Surprisingly, a lot better than I thought it would. But that's one of the things we do is a lot of R&D work when there's a challenging application. That's what kind of my guys in the office geek out about. And the only thing they geek out these days to me about is the fact I haven't bought them a QTec. I always rely on Osama to loan me one. So, but nevertheless, you have parts that need to be tested, send them our way, and Osama and I will get together and do a little R&D to see if we can solve your problem. But so just a long history of different applications. Won't bore you too much on that, but gearbox driveline applications, brake rotors, brake pads, wheels, various gearboxes, camshafts, and so forth. One of the coolest applications we have, I don't have a good video of that, but right now, but is we're big in the car seat industry, the frame, and frames and metals, but not so big in the trimmed seats, just because it's difficult to get an accelerometer in on the seat to get the measurement. Whereas we started using the QTec to actually aim at the leather material. And now then, in some of the high-end seats, there may be 30 different actuators or components inside the seat for heating, for lumbar support, for fans, cooling, various leg extension, all kinds of different applications, headrests, power headrests. We found out that through one of the R&D projects we did was that we could take the QTec and aim it at parts of the leather surface of those seats and really identify any of these complaints that were in manufacturing defects that were showing up on that particular seat. So just another application where just the slightest amount of vibration that you hear is being emanated through the surface of the skin of the leather material, and the QTec's picking that up and identifying it for us. So then we just write a little metric around it and maybe add a little AI to it, and boom, we've got a really great solution with with probably the only tool in the world that can solve that particular problem. Previously, you had to spend $250,000 on a very quality laboratory grade sound booth that you put in on an assembly line. And maybe you had to buy 4 or 5 of those on your assembly lines to keep up. And it just doesn't, and on top of it, you're probably using subjective type listeners that some people heard it, some people don't. So now you're also dealing with subjective versus a very good quality objective measurement. So I'm going to get into just a couple of quick videos, and we'll be kind of wrapping this up. But here's that casting thing. Over here, there's a, let me turn my pointer on here. So over here we have the part under test, the target that we're trying to hit with our laser. Well, that over here, it's like 600 degrees Fahrenheit, and there's flames going and steel popping and so forth, and that turned out to not be a good thing for lasers. the lasers are tough, but once you start pouring molten steel over them, they tend to run into some problems, as well as the computer systems. So we wanted to launch this thing 16 feet away from the surface. So you'll see in here, there's a tube that's going to go up and down, and it's controlled by the PLC that tells us which part number is under test, so we know where to aim for the particular wheel that's being manufactured and so forth. And then this has been in place for 10 years at least, maybe longer, in several different plants across the United States, Canada. So it's really does a pretty good job. So let me see if I can gotta go out of my point of own. Sorry about that. And so you see the part go up. It's aiming at that little, you can see in the file here, it's aiming at that little dot, which is where the laser is pointing. Making the measurement. It's identifying when a porosity occurs, there'll be a lot of vibration, a lot of air trapped in that kind of pops and so forth as the porosity starts forming during the casting process, and boom, it really falls out pretty nicely just because of the ability to, from so far away, get that laser pointed. Here's another cool little application where we have this video, and I'll mute myself here real quick.
This is a short video describing our proposed weld inspection for the carbide tip blades. Theoretically, every carbide tip will have a family of mode shapes that will be affected by the presence of a poor weld. The resonant frequency of these modes are computed as 1/2 pi times the square root of K over M, where K is modal stiffness and M is modal mass. Our experience in production is that the modal mass will not vary as much as the change in stiffness when there is a defective weld or crack in the joint. This application does, however, create several challenges. First, how do you make the measurement on such a small component? Our response is to use the laser vibrometer from Polytec as our measurement device. Second, how does one excite the resonances of the tip without overwhelming the entire signal and trying to only excite the desired modes? We have tried several methods, including a small tap test, a little forced relaxation technique by flicking the part, and what we are going to demonstrate here is a magnetic field driven with the swept sine function that targets our inspection to the frequencies of interest. In this example, we are sweeping from 5,000 to 15,000 Hertz. Third, we are currently under the belief that we need to test every tip. This demo is the best we can do without spending a lot of R&D money. And finally, test time has not been optimized on this setup. As the magnetic field excites the system, the blade tip will go in and out of resonance. The premise is that all tips will have similar local mode shapes, but the frequencies will all vary as not one weld is identical. However, the defective weld or cracked joints should have a very significant signature. Let's take a look. The servo drive steps each tip in front of the laser vibrometer, and once focused, the system triggers the HP signal generator to output a swept sine signal to the piezo device. That then excites resonances of the tip as the sinusoidal forcing function sweeps from 5,000 to 15,000 Hertz. The response of the tip is captured by the digital signal analyzer and then inspected for abnormalities associated with a defective weld or crack. The best we have been able to do is remove some material to simulate a defective tip. The differences in the metric value can be seen from a drastic defect to a smaller defect.
So I'll move on here to a gearbox test application.
The Signalysis IQC Gearbox solution performs quality checks to guarantee customer satisfaction and avoid warranty costs. SigQC measures vibration as a function of input shaft speed and performs order domain analysis of bearings and gear mesh frequencies.
The machine uses a non-contact laser vibrometer from Polytec that's so accurate it not only tells you what gear has the problem, it can tell you what tooth has the problem.
These signatures can be further analyzed to 100% inspect for manufacturing defects for gear noise, bearing noise, roughness, and other quality checks. The result is a traceable set of NVH data used to perform go, no-go on 100% of the gearboxes produced. These test results provide manufacturing engineers with the data needed for Six Sigma studies and continuous improvement objectives.
And then we move on. So that's a lot of the dynamic testing. Now we look into some of the other frequency inspections of castings and so forth. Again, in the world of brake rotors itself, we found that the demand from the OEMs is going higher and higher in frequency and trying to get even more of the more difficult modes to the in-surface or in-plane modes to catch. Those require, really, the QTec is, like Osama was pointing out in his slides, picking up some of those measurements is really a piece of cake with the vibrometer and so forth. So we'll here's some of the mode shapes we're talking about, some of the issues with brake pads looking for cracks and safety issues associated with delaminations and so forth on that. And more brake rotor type applications, again, getting up in the higher frequency range and so forth. And let's see, here's a cool camshaft application where we're looking for cracks to be found in camshafts themselves and in the lobes of the camshafts. Really turned out to be a great tool for whole camshaft health when you run into issues of porosity and so forth as well in that. So, and one of the other cool applications you'll see here is, I'll try and point this out, is you'll see these the laser dot on the side of the camshaft lobe, but we're having to use the mirrors. We worked with Osama and Polytec.
Camshaft will lift up into place, we'll rotate it, and we'll use this gear to index the shaft in the right position. At that point, the lasers will be mounted to fixtures up above, and then the hammers will be in place to come in and dean each lobe. So what we'll do is when every lobe gets hit, we'll gather vibration data off all of those, and it'll go bing, 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 all the way down the line, and we'll pick up all 8. So we'll get a set of data that we'll feed all into our algorithm, which then is going to be able to break down and separate out cracks. And what we're looking at, which you'll see in some of the FEM models, is when the lobe itself starts twisting or bending. So anytime you have the miniature cracks anywhere around this lobe, that's going to change the stiffness dramatically for the lobe itself, and that's going to drive the resonant frequency down, because resonant frequency is 1/2 pi times the square root of K over M, where K is stiffness, M is the mass. Your structure is very repeatable and very precise. We're not seeing much difference at all with the modal mass that would drive frequencies around. So the only thing that can make our frequencies move would be the stiffness and so forth. And so we have some, by gathering 8x8 matrix of data, we've got the opportunity to do some serious analysis and
Neil, I believe you're muted at the moment, so.
Very good. Thank you very much,
Thank you.
Isabella. So, yeah, the last thing I want to do is talk about another application where we wanted to improve on how we were doing our tests And so we implemented some robot and some automation and then took advantage of the QTec, the surface of the, let's see. Oh, where am I? Here we go. Sorry, guys. So this right here, this surface finish of the lobe is not finished. It's just a straight casted material. And using the single point laser for that turned out to be a real challenge. In fact, having a lot of signal to noise issues and so forth on some of the tests. So we then invoked the QTec laser to come in and save the day, and then added a little automation. So when I show you this movie, if you'll watch this, if you'll watch the laser, where it went to right there, if you'll watch the laser, you'll see it increment up and down. On this movie, you can see it move, and then on this one, you'll see that the green dot, which is the laser pointer, or where it's pointing, will step through all the different lobes. So I'll try and, these won't really be synced up, but we'll do the best we can. And maybe I can so you can see that really gave us, that was just a game-changing moment as well with the QTec. And the cost, was really just minuscule compared to savings that you get in the speed of the operation, repeatability, and so forth. So with that, I think I'm pretty much done. Back to you, Isabella.
Perfect. Thank you, Neil and Osama, for your excellent presentations. And now Craig will begin the Q&A session. And as a reminder, you may continue submitting questions in both the Q&A box and in the chat box. Thank you.
Thank you, and thank you everyone for joining us, and thank you Isabella and Polytec for hosting today's webinar. And again, thank you Osama and Neil for the presentations and insight today. At this point, we'll open up things for questions from the audience. If you have any questions, feel free to submit through the webinar chat or Q&A panel, and we'll do our best to address as many as we can. We'll give everyone a moment to submit some questions. We did have a couple pop in here. First question is, what types of applications benefit the most from moving from contact sensors to non-contact measurement?
You want me to take care of it? I can answer this one briefly. Yeah. So when it comes to the applications that benefit from moving from contact to non-contact, honestly, it could be all of them, but mainly I would say the ones that they have a critical mass where you don't want to touch it, you don't want to add anything to it. So I would say medical, biological applications, and production or R&D. These are, I would say, some of the main applications. And the other ones, of course, the higher frequency, where normal contact sensors are not capable of reaching.
All right, next question. Can we connect a point LDV as one of the reference channel in QTec LDV?
Yeah, I can answer that as well. Yeah, so any single point system can be used as a reference with any other type of DAC, or for example, if it's with a scanning system, it can be used as a reference to capture the phase and the amplitude information. I hope that answered the question.
Let's see, next question. Do you have any recent case studies implementing AI and ML models for noise source identifications using either LDV, accelerometer, or microphones? think this was a Signalysis question.
Okay. Yeah, we do have some applications. Robbie back in our office is working on quite a few applications in the AI, building up some models and some using machine learning and so forth. And the one nice thing you get out of a production test environment is a lot of data. You know, you can, it's coming, that data is coming daily, and you can just keep throwing it in the model if you need it to and so forth. But as from a series of testing, brake pads, brake rotors, you know, he's getting some really good work done. So yeah, I'd be happy to talk to whoever about bringing that in and showing you how we, you know, the work we can do.
Someone asked if it was possible to review the recording later, and yes, it will be available later on. Next question. Can you give an example where vibrometry solved a problem traditional sensors struggled with?
Yeah, I think I can probably comment on that from experience around the laser vibrometers. Most of the here, I think when it comes to measurements that are so impossible to do with contact or so difficult, one of them is, which could be two opposite, underwater application where the laser can measure under the water. It could be a cold environment. The other opposite extreme is the super hot surfaces. The laser doesn't care about temperature, so it can measure as far as we put it at a safe distance or put it in a cooling housing if it's very close to the molten steel, let's say, where it's so hard to put in a contact, let's say, accelerometer. One more application I can think of right now is the wind turbine. At very long distance, you want to measure it from the ground, for example, a certain location at a bridge. So there are multiple applications where it's impossible to use a contact sensor that the laser can do the job so easily.
Another question. In the software snips where you showed the gearbox testing, would like to know more details on how the IVS is connected to the system. Is it analog or digital mode?
Actually, in that application, that's a good question. I meant to comment on that. We're using the digital mode of that, and we take the tachometer from the shaft or from the encoder and feed it back in. There's a trigger function on the laser vibrometer, and we're able to use that as a trigger to do. There's no data acquisition involved. We just feed the data directly in, and you can start doing your order domain analysis directly.
Next question. How difficult is it to integrate LDV into an existing production environment?
Simple, I said. Go ahead,
No, I mean, that question goes to you. It should be simple.
You know, we do that quite a bit. We maybe there will be parts coming down the line, and there's a functional test station. We've done it like with recliners, for instance. There are parts coming in, and they're experiencing an actuator issue. They're trying to subjectively listen to it, either put their hand on, have an operator listen, or put their hand on the part to see if they can feel it vibrate. And subjective is just that, subjective. Everybody has an opinion on whether something's good or bad. And normally in a manufacturing environment, the guys working on the assembly line are trying to fill a truck full of parts, and they have quotas and numbers that are being watched every minute of how many parts I accepted and pushed off. So there's always a weighted subjective to completing the job, you know. And but we're able to just walk right up with the laser in a tripod, you know, and set it up and run the test and show people how it works. So it does work pretty good. It puts on permanently. Sooner or later, you want something fixtured up, you want to study the floor vibration to make sure it doesn't come in and affect your measurements. But yeah, it's really pretty easy. I don't, Osama, you might have more to add on that.
No, I think you covered it all. Yeah, thanks a lot, Neil.
Next question is for Signalysis. Considering the wheel production test that Neil highlighted, I'm wondering what kind of failure rates the customer was experiencing that led them to implement the solution. Is there anything to be learned from the measurements that leads to a process change? What are examples of process variables that the customer adjusts as a result of the LV measurements?
You know, some of that I can't comment on because it's confidential, but there was anywhere between 20 to 30 wheels that would be missed, or they would eventually catch it, but then they would have to go out and do a sort of the parts that were produced after that or before that to figure out when the problem occurred. And I don't really know all the details internally on the discussions they had about other issues of other ways they could contain or prevent that problem from happening. But it's one of those things. Once it starts happening, it's going to continue. It just gets worse and worse and worse. And so, yeah. Sorry, I probably didn't really answer the question the way you'd like it to be answered. But shoot me an email.
Next question. Do most customers begin using vibrometry in R&D environments first or directly on the production floor?
I mean, I can probably start that. So I think it depends on the application. It could be both, and depending, I would say, on the level of data that is needed. So for example, the scanning vibrometer, I would say most or majority of applications are related to R&D because they want to see the mode shape, they want to see more details, measure the part from different locations. As a single point, I would say this one, especially IVS from the name industrial, this one goes straight into the production line, but we still have a lot of customers that use it in the lab as well. So I would say both, and that same unit that is used in the R&D can be moved to a production line as well.
Yeah, I might add to that from our side, when we get involved, a lot of the manufacturing facilities don't even understand, don't have a clear picture of what a laser vibrometer does. And so they rely on us to kind of help point them in that direction. But then if it's a company that has a big R&D or a big NVH facility, a lot of the engineers that are working in that environment are starting to say, hey, we want to put a laser vibrometer on the assembly line at our manufacturing facilities, because they understand the power of the laser.
I think this next question is probably similar to that. For companies newer to vibrometry, what's usually the biggest misconception about implementing non-contact measurement?
To me, I can comment shortly on that. It's one of the things that is, I would say, maintenance free. That a lot of people think if I get it, I have to do maintenance. It could be a one-time installation and all set. So a lot of people might think it comes with a lot of maintenance or follow-ups on checking the system. But that's one thing a lot of people probably miss is it's a maintenance-free system. You just install it one time, should be all set.
Next question is for Polytec. What are the constraints related to the surface condition that's optimal for LDV use? What surface types will be challenging to make measurements on?
So luckily, yeah, with a QTec technology, honestly, there is no need. I know back in the day, probably in the 90s or the early 2000s, when the red laser was the only thing available. But now even our red laser for scanning could come with a QTec technology. So with the QTec technology, there is no surface that is non-measurable or needs to be treated.
just giving everybody a few more minutes if any more questions come through. All right, I don't know how much any more questions are
Yeah.
coming through.
And if any question comes up later, we'll definitely send a follow-up email with our contact information. So anything that we couldn't answer today, or there was no time to address it, we'll be in touch.
Yeah, I think that I was going to say we can conclude the Q&A. So thank you again, Osama, Neil, Craig. Thank you for moderating the Q&A. It was a great discussion. And of course, thank you everyone who attended, joined us today. We appreciate all your time and participation. Thank you for your attention and all have a wonderful day.
Yep. Thanks everybody for attending, and really thanks Isabella for putting this together.
Thanks,
Of
everybody.
course.
Bye-bye.